I'd like to welcome Jeannie Larson, who's applied to join us as a associate research scientist and currently at SETI, but living in Utah. And so she'd be number 2 in Utah. So Jeannie, looking forward to your talk about bashing things, and I'll turn it over to you.
Awesome. Thanks. Yeah. Happy Pioneer Day to the one other Utah person here. Yeah, so I know on Zoom it says I'm at UCF. I'm not at UCF anymore. I am with SETI now, but would love to be working with PSI, um, doing a bunch of impact work, honestly. Um, in case you couldn't tell by my first slide, I am a huge nerd and I love comics. Um, And so, as such, I will be talking to you about different impact scenarios on binary asteroids. Um, so, binary systems, looking specifically at binary asteroids, there are at least around 500 of them known as of like last February or 2 Februarys ago at this point, I think. Um, we know we keep discovering them. One of the more famous ones that's been known lately has been Didymos and Dimorphos because of the DART mission, which I'll talk about a little bit later because it's kind of the inspiration for this whole project. And there are really 2 formation mechanisms of these binary systems. So one is kind of a collision between 2 bodies. So if you have 2 small bodies that collide, then one kind of ends up either bouncing off or they accrete and another chunk comes off. And in this case, the primary body will tend to have a really long rotation period, which I promise will come into play later. The other case is rotational disruption. So if you get a body that starts rotating really fast, usually it's faster than like 2.3-hour rotation period, then it can reach that critical limit and basically tidally tear itself apart. And then you'll get basically a little asteroid moon kind of forming off the side of it. And so in that case, you end up getting a primary body that is rotating near the critical limit. So really rapid rotation period.
Excuse me, Jenny, this is Mark. Does for that rapid rotation thing to work, does the asteroid have to be a rubble pile, or is the rapid rotation sufficient to, like mechanically break the thing?
It is sufficient to mechanically break it, like once you get going fast enough.
Hmm.
I don't believe it has to be a rubble pile.
Okay.
Um, so, kind of switching gears a little bit from binaries to talk about my other love, impact modeling. So, I love this diagram here because it kind of shows the whole process of impact modeling, where we look at lab experiments, and this we can validate with different shock physics codes, and we can also use that information of these images to create different scaling laws. And kind of the shock physics code combined with these scaling laws help us create n-body codes and other forms of like larger scale ejecta evolution, which is really what I love looking at. So some of y'all may have heard of ISAIL. I saw Jack Conrad on here, so yeah, I'm sure you know ISAIL. And that's more of like a shock physics code. So that is looking more specifically at the actual crater formation itself, along with a little bit of the ejecta coming off, but it doesn't necessarily look at this large scale ejecta evolution in an entire system. So on the right, there are these different types of models. One's an n-body code, and one is a smooth particle hydrodynamics code, or SPH code. Both of these are really great, really well established at basically monitoring how particles move in the system. Both of these were actually done for the DART impact experiment itself. So here you have a nice little binary system with the impact on Dimorphos, and we can watch as basically these tracer particles evolve over time, and we can see where the particles land. Similarly, you can do that with PKD grav, which is an n-body code, which basically looks more at individual particles. It gets a little bit tricky with n-body codes because while you get the benefit of like looking at specific individual particle interactions, it can be really difficult computationally, which is why I ended up writing my own and forgot to put a slide in for it, of course. But I'll talk about the code that I wrote a little bit more in the future, but I use basically a program called Rebound, which is a Python program. I know a lot of people have different feelings about using Python for coding versus using the standard Fortran that a lot of other people use still. But yeah, so Rebound is really good. It has a Python version, a C version, and so I wrote essentially a package for it, the Rebound Ejecta Dynamics package, that can run these n-body simulations. So basically create simulations like this first SPH code one, but using an n-body integration scheme and looking at the individual particles. Yeah, so I'll be talking about that throughout because that is the code that I end up using for all my simulations and stuff. So, impact experiments, this was essentially my inspiration for the project, looking at the double asteroid redirection test, the DART mission. I did a little bit of the preliminary modeling on this project using the code that I wrote. And so a lot of what I end up basing my binary system on is the Didymos system. The reason for that is now we have lovely pictures of an impact in a binary system. We've had impact, like the deep impact experiment was done on just a single body. That was wonderful, but now we can really see in good resolution, as good as resolution as we can see here, basically where the ejecta is going in this binary system. And we'll have Hera going in 2026, I believe. I think it launches 2025, but we'll get there and actually do studies 2026. Hera will be following up to like look more at the changes in the surfaces, kind of where the ejecta landed after it created this gorgeous spiderweb-like plume, which is really kind of what ties into what I do is I look at where the debris lands on the surface. So I can trace the particles through their full evolution and then basically map where it lands on the surface, where we would expect to see kind of those different surface processes. So some of the big questions, or three big questions anyway. Are there certain binary system parameters associated with distinct ejecta patterns? So do we see different ejecta distributions on the surface due to the binary system looking a certain way or having different forces in play? Also, how do we expect ejecta to interact with binary systems with varying mass ratios? So this is kind of like specifically what binary parameters can cause these different things, these different patterns. So looking at specifically the mass ratio between the large body and the smaller body, and looking at the primary rotation periods. And then finally, what do the ejecta blankets that we're observing tell us about the dynamical history of, sorry, my cats, they're special. What do the ejecta blankets tell us about the dynamical history of a binary system? So we have we start with a general setup. A couple things that are a little different from what I'm modeling versus what the DART experiment looked at. The DART experiment had the impact on the secondary body, and I'm doing it on the primary body. So it's a little different, but still looking at binary system. So we have essentially an ejecta cone that is coming out of some sort of location on the primary surface. We do use an ellipsoidal body because it's slightly more realistic. So we look at 3 different locations. One is like directly underneath where the secondary body is. One is at 60 degrees north, so a higher latitude. And then the other location is like 90 degrees from where the secondary body starts. And that's just because the first time I ran the simulation, I started at 0, 0, and it was kind of like, okay, well, that was fun, but we might be seeing more influence from the secondary because we're starting directly under the secondary. It's also not super likely that we'll end up having an impact right underneath where the secondary is, just because of practicality of like, okay, so if something's coming into impact, it would have to pass by the secondary, basically. So we keep essentially a tidally locked secondary body, which tends to happen a lot in binary asteroid systems. And then our target body, we vary the rotation period, and our secondary, we vary the mass of it. So essentially what we're doing is just varying the rotation period and the mass ratio. So if we have a really fast rotation period, so 2.3 hours, and a mass ratio of 1, which basically means your secondary body is the same size as your primary body, you're going to get the most influence from the effects. And so this is kind of where we look at to say, okay, if there's a ton of effects in the system, what do we expect to happen? Which effect do we see kind of more dominant than the other? On the opposite side of the spectrum, we have basically a 1,000th the mass of the primary and a 12-hour rotation period. So this is where we have the least influence from effects. So almost no influence from the secondary body and basically no influence from the rotation period. So this, we should be expecting what we would normally see from an impact on just a single body.
Can I ask a quick question?
Mhm.
You said ellipsoidal shapes are used. Are they prolates, oblates, or triaxial?
These are oblate, I believe.
Okay,
Yeah,
thanks.
I have it set up to be able to do triaxial in the code, but this specifically, I believe I used just oblate.
Okay, thanks.
Mhm. So, all right, now we get into the fun pictures. So looking at a rapid rotation case. So all of these simulations have a rotation, primary body rotation period of 2.3 hours, but we are varying the mass ratio, so changing the size of the secondary body. So we start out with almost essentially the rotation period being the sole effect with a very small secondary body. And we see this really cool kind of like swoosh pattern where this little red star, I should have made it bigger, but the little red star is where the impact site is. So it's not directly under where the secondary body is. I've learned from that mistake. And it's not exactly on the equator. So it's a little bit above the equator and almost on the opposite side of where the secondary body is initiated. And so we end up seeing kind of this leveling out of particles trying to basically flatten themselves out along the equator due to that fast rotation period. And even as we increase the mass of the secondary, we continue to see this pattern of kind of like downrange spray along the equator of the particles along the surface. It starts to get even more interesting as our secondary mass gets larger, because we actually see the secondary mass pulling the particles even farther around. So we're not changing the rotation period in any of these. We're just adding in a slightly heavier secondary that ends up kind of swinging these particles around and causing this weird little like circular vortex thing. And as we get to our like almost equal mass, so like half the size of the primary and the same size as the primary, we start to see that the particles aren't being swept around the equator anymore, really. They tend to stay a little bit closer to the impact site, which was a little puzzling initially. I thought that I did something wrong, so I ran those simulations a lot of times, and kept getting similar results of these particles don't fully get wrapped around. And the reason for that is because the secondary is now controlling where these particles go. So rather than having the rotation period kind of sweeping these particles around on the equator, we end up getting more of an influence from the secondary, where these particles are just essentially getting lofted and kind of pulled back, because the secondary body starts about here and is going to move this way. So as the secondary body's here and these particles get lofted, they want to be pulled back towards the left a little bit. So moving on to look at a slow rotation with varying mass ratio. So instead of having the 2.3-hour rotation period, we're looking at a 12-hour rotation period. Because of the slow rotation, we don't see a lot of the sweeping around the equator, which is fine. We didn't expect that we would see that. We do see a little bit of kind of elongation from the impact site initially. As we end up adding in a larger and larger secondary, we really don't see that much of a difference, except for in this equal mass case, where if you stare at it long enough, you can actually see that there's less downrange spray, and it's actually more centered, the ejecta is more centered around the impact site. And so that's kind of similar to in the previous slide here, where we see that these particles aren't being swept around the equator anymore. They're kind of just staying localized. So it's not quite as exciting here, but still interesting. All right, kind of switching gears. We're now looking at how the rotation period is going to change what we see. So in these cases, we kept the secondary body as the smallest size, so 1,000th the size of the primary body. So there's almost no influence at all from the secondary body in any of these cases, and we really just see influence from the rotation period. So starting off at the 2.3-hour rotation period, again, we see that kind of swoosh around the equator, where the particles kind of get wrapped around the equator and are trying to balance themselves out. As we increase the length of the rotation period, we see that less and less, which is expected, because we have less rotational effects going on throughout these. So it gets a little more interesting when we add in an equal mass secondary. So this is a secondary that's the same mass as the primary body. And we tend to see that the secondary body in these cases almost completely dominate over any rotation effects. So again, in this 2.3-hour rotation period, we'd expect to see particles being wrapped around the equator, and we're not seeing that here because our secondary body is basically holding them back and keeping them localized. Same with the 3-hour rotation period, 4, 6, 8, 10, and 12. Part of the reason why the ejecta gets more and more localized, though, is because we are slowing the rotation down. And so as we slow the rotation, it is going to stay more localized anyway. We're just seeing an additional influence from the secondary body kind of holding it back a little bit. Okay, so all those maps are great. That's cool, but what else can we do with them? So sure, we can look at a map like this and say, okay, if I see an impact on a body in the system, we should see ejecta falling in these areas. So we should see a blanket in this spot. That's fine. But we can do more with this. So we can look at the percentage of the surface coverage. So how much of the body, the primary body, is actually covered. And so here we have basically the mass ratio on the y-axis, basically going from our smallest mass ratio up to our largest, which is the equal mass, and then going from essentially the smallest rotation period up to our fastest or slowest rotation period. And so as kind of expected, we see very little surface coverage on the 12-hour rotation period. And that's basically because we aren't seeing particles being wrapped around the surface. They're staying very localized. As we get to faster rotation periods, so less than a 6-hour rotation period, we start to see more and more surface coverage. And that's kind of to be expected because we're seeing particles being wrapped around the equator there. What's interesting is combining that rotation period with the mass ratio. So when we look at the mass ratio, as we approach kind of like the 0.1 mass ratio, we end up seeing that there's a lot of surface coverage. And if you remember from a few slides back, this case here. So this case has a lot of particles being swept around the equator, and it's also heavily influenced by that secondary body, which is kind of wrapping particles around in this little weird circle right here. So we end up seeing around like just over a 30% surface coverage. What's kind of unexpected is as we increase the mass ratio, we actually see less surface coverage. So part of this is because now we're, as we have a fast rotation, we actually have the secondary body kind of holding particles back, keeping them more localized. Also, in these cases, we tend to see more particles being lofted and not ever really impacting the surface again. And we see that here in this case, where looking at this scenario, this is going to vary depending on what type of impact it was. It's going to vary on a lot of different parameters, but for the simulations that I ran, pretty much all of the particles landed on the surface somewhere on the primary, except for in this nice little case up in the corner where we have a high rotation period and an almost equal mass ratio. And in this case, we had like around 60 to 70% of the particles landing on the primary body, but not 100%. So there are some particles that were lost, some that ended up landing on the secondary body, which is something that I haven't mapped here. I have the capabilities of mapping, but I just didn't do that in this particular study. And then if we also look at the maximum particle distance from the impact site, we end up seeing kind of similarly, particles travel the farthest when there's a fast rotation period because they're getting wrapped around the equator. Particles tend to not travel as far. They tend to stay more localized to the impact site when you have a really large rotation period, so you're rotating really slowly. And then we get this case where we have the almost equal mass ratio or equal mass ratio, where particles aren't traveling as far. And that's because they are being attracted more to the secondary body rather than getting swept around by the rotation period. And so this allows us to see kind of when different effects are dominating. And so we can kind of use the edge of the yellow here where particles travel the farthest, kind of say, okay, in the cases where it's like yellow and we have the maximum distance traveled, we tend to see rotation being dominant. In these other cases, we tend to see the secondary body being dominant. So we take our big questions and we come up with big answers. Some of the big answers that we have are that at a high spin rate with a mass ratio close to 1, fewer particles are going to land on the surface. And they're really not going to travel that far from the impact site themselves on the surface. Most surface coverage we see is when the rotation period is less than 4 hours. The mass ratio is around 0.1. What do we really expect? How do we expect ejecta to interact in binary systems with these varying mass ratios and primary rotation periods? Well, we can fairly confidently say that the rotation period tends to dominate the outcome if the secondary body is small and the rotation period is slower or faster than a 6-hour rotation period. However, the mass ratio tends to dominate if the rotation period is going to be slower than 6 hours or the mass ratio is really close to around 1, so really close to equal masses of your two bodies. And most importantly, what do these ejecta blankets and these maps that I made really tell us about the dynamical history of a binary system? So why this is important really is we can look at different objects and different craters on those objects and kind of trace out their ejecta patterns and their ejecta blankets. If we find an ejecta blanket that is really characteristic of a fast rotation, but the body's rotating slowly, we can assume that there's something that happened in there that could have caused the body to slow down at some point in its history. Whether it was that impact specifically that helped cause that or not, completely different, but we can kind of like trace back using these blankets and kind of test what happened dynamically. So a couple future projects, which if anyone wants to collaborate, I would love to talk. One is looking at the formation mechanism of equatorial ridges. So previously, a lot of the formation mechanism has been thought of as you have a body spinning up and kind of the accretion of a disk, or as it's spinning rapidly, you end up getting kind of a landslide out along the equator. Sometimes that can form a moon, and the moon is either lost or it remains. This is Iapetus, which is famous for its nice little ridge along the equator. So if we look at large impacts on fast rotating bodies, we do see a large amount of deposition of materials along the equator, which could, in some cases, be a cause of an equatorial ridge. Not always, but potentially in some cases. So it might be worth looking into just seeing, okay, do any of these bodies have some sort of large impact that could have created some sort of structure like that? Or is this mechanism of the landslide along the equator the most common that we'll be seeing? And one of the projects that I'm currently kind of starting to work on and working on a proposal for is looking at adding particle interactions and atmospheric effects and gas effects into the Rebound Ejecta Dynamics code. So looking at particle interactions, there have been a lot of lab experiments and different studies that trace basically the speed, the relative velocity of different particles in a plume and what happens to them. And so in certain velocity regimes, we can see the particles will just bounce off of each other. As you get to higher velocity regimes, we start to see different things. So you can either get partial fragmentation where one of the particles will break up slightly. You can get all the particles just kind of obliterating themselves if they are colliding fast enough and are kind of weak in strength. You can also get the particles accreting onto each other and forming just one larger particle. So that's something I've been working on adding into the code, because that does actually change later on your size frequency distribution. And so it could potentially change those maps that I make just a little bit. The other one is looking at atmospheric effects. So currently, Rebound Ejecta Dynamics package can only be used for looking at airless bodies. But it would be wonderful to be able to apply this to almost any impact. And so I've been looking into kind of adding how to add in different drag forces, turbulence, which is annoying, and kind of how particles get lofted over kind of the changing airflow underneath a crater. So one thing that has been really useful, and I don't know if anyone saw the Yellowstone eruption that was announced, but I honestly love the video of that and would love to model some of the debris coming off of that because it is a great volcanic plume. But yeah, volcanic plumes can be used as kind of an ejecta analog in that it's hot debris that is being lofted into the atmosphere with gas, with other debris, and it does experience some sort of drag forces. So we can use kind of the atmospheric models that a lot of volcanic models use to kind of apply that to what I'm trying to do with ejecta. And that would allow us to look more in depth at large scale impacts, such as like the Chicxulub impact and how particles kind of got lofted in that case. and what happened there. So yeah, that's what I'm working on. If you have any questions, I'm happy to answer or discuss or whatnot.
Thanks very much, Ginny. Appreciate your talk. Very interesting. Are there any questions?
Yeah, I have a question about that. You said observationally, if you see, you have an ejecta blanket in a certain region, then you can go back and say, oh, it probably had to be like this. But how you only can do that if the ejecta have different properties, right? Or different material. Otherwise, you can't distinguish it from what's already have been there. And also the other thing is, what if you have multiple impacts? How can you distinguish what's what? Which one belongs to which impact?
Mm-hmm. Yeah, that is the tricky part. And that comes from honestly years of practice staring at a lot of impacts. Some ejecta blankets are really easy to look at and kind of distinguish where the outline is on the surface. A lot of them end up getting covered up by different craters and whatnot, which is really annoying because it's hard to trace where that material comes from. It can be the same material as what's on the surface. It ends up kind of being, if it's a large enough impact, it does end up getting like reset time-wise, if that makes sense. Because you can shock the material enough that it will kind of reset the isotopic clock on the ejecta. And so the age of the rocks from that ejecta blanket should be a different age from kind of the base surrounding rocks.
So that means you need an in situ, you need to go, or you need a spacecraft to go measure the isotope ratio. I mean, I'm thinking of observing the stuff from the ground.
Yeah,
that's what you mostly have to do.
Yeah, and that is tricky. There are some ways of just like, again, just like looking. This is usually what a lot of undergrads end up doing, is staring at maps and circling where the ejecta blanket goes around different craters and kind of saying, okay, I think this ejecta belongs to this crater. And that is also why ejecta modeling is so wonderful, is because if you have a really large scale old crater, you can compare even with other models that kind of say, okay, given these current conditions, this is where we should find some sort of ejecta blanket. And then if we look there, just like looking straight at a picture of it, we can sometimes trace where the ejecta might have gone, but it does get tricky.
Thank you.
Does the ejecta, like with the DART mission, after the impact, was there now I don't know if light curves of the two bodies were separable and measurable prior to the impact by like Hubble Space Telescope or something like that. And if they were, then were they observed again after the impact to see if there's a difference in the light curves of the two bodies? Certainly on the primary, the difference would be due to the accretion of ejecta material, assuming that perhaps the scattering properties of the dust, because it's fresh and ground up, and maybe smaller stuff, might make portions of it brighter or something. And so has any of that kind of work been done to your knowledge?
I'm not totally sure about that. I'm guessing someone in one of the working groups has looked into some of the light curves.
Yeah.
I know it's really hard because like all our most of our observations are ground observations. And it's so hard to distinguish the two bodies.
And when Hira gets there, then based on maybe looking at other small bodies, like Bennu and whatnot, how would Hera, what would they be looking for in order to just to see an ejecta plane? Would they expect, different scattering properties? And so, it's a bunch of smaller stuff that's going to be over this area, and therefore we'll look for that.
Yeah, so with Hera, we have a lot of pictures of the surface, thankfully, after, like, just from ground observations and also from the approach, we were able to get a lot of pictures. And so we should be seeing differences in the materials that were deposited recently versus what used to be there.
Right. Right. Yeah. So they don't even have to be different scattering properties, because if you're looking close enough, you're going to see, oh, look, there's a lot more garbage here. So,
Yeah.
Okay. Okay. Yeah. Interesting.
Different garbage. Mm-hmm.
Yeah. Yeah. Any other questions for Ginny?
Yeah, I have actually a couple of questions. Thanks, Jenny, for a very interesting talk. So this magic number around 6-hour rotation, I was just wondering if you have a large primary, both mass as well as the size, whether that number 6 hours can vary. That is the first question. And the second one relates to one of the earlier slides that you had with number of panels. If you could go back all the way towards the very beginning, maybe one more, maybe one. Yeah. So basically, you're using different masses, so of mass ratios. For the top left is basically the secondary is very, very small compared with the primary. So essentially, by looking at this sequence, the top left is maybe the result you are getting if there is no secondary.
Mm-hmm. Yep.
I was just curious. More than 20 years back, Paul Geisler did, I can't remember exactly whether it was IDA or GASPRA, ejecta fallback distribution. I was just curious, you may want to check whether it is compatible with what he got.
Sure. Thank you.
So do you have any comments on the first question?
So this is an ongoing project as well, because the mass ratio and the rotation period aren't the only two things that are affecting a binary system.
Yeah.
Parameters. Yeah, I would love to continue this study, and that's something that, like, I do want to submit a proposal saying, hey, look, I have this study. This is interesting. Now we can expand it and make it into something even bigger. We can look at the large mass, because I have a feeling that it's not just a magic 6-hour rotation period, because there are cases where there are incredibly slow rotation periods, like 24-hour rotation periods, and I didn't look at that in this study. And that might affect it. Having a large mass in general of the body might affect it, especially with comparing, like, the impact energy to the mass of your primary body. That's going to be a huge difference. And here I pretty much just took roughly the impact parameters from the DART mission and a roughly Didymos Dimorphos based system. So my primary here is about the size of Didymos.
Okay, thanks.
That was a really long-winded answer. I'm sorry about that.
Gusto.
Yes, hi, this is Augusto Carvalito, and thank you for this very interesting talk. I was curious about, maybe I missed it in the beginning, but how do you choose, or how do you determine the properties of the impactor?
That's a great question. So in this particular study, it was kind of inspired by the DART mission. So taking the impact parameters from the DART mission, an impactor that's roughly the same size, roughly same velocity, looking at the actual parameters of like different parameters of an impactor and how that impacts the impact energy itself is definitely a different approach. So there are ways of, if I changed the impactor itself, it would change the impact energy. So there are a lot of different things that can kind of affect what happens to the impact itself. So if you have a really high velocity impactor, you're going to get kind of a larger plume. Similarly, if you have a large object that's moving slow, you're going to still get a huge plume. And so at that point, it kind of breaks down to what is the energy of the actual impact itself based on these different parameters. So that would be something that honestly could be like a study in itself. I'm sure I know people have done laboratory experiments before looking at different material properties of both the target body and actually of the impactor itself, and how that plays in. Here, I kept it a constant impact energy the same the whole time because I wasn't quite looking into that. Does that help a little bit?
Yeah, definitely.
Okay.
Could you do ice?
That would be cool. So I haven't done ice yet. Ice kind of scares me. I'm kind of a just small dry body person right now. Ice is fun because you end up getting like a lot of, you can correct me if I'm wrong, but a lot of like gas and vaporization happening. Which is partly why I really want to add in like the gas effects to the code, because then we don't have to work with just small dry bodies. We can play around with comets and other fun objects.
Right. Thank you.
I seem to recall from ancient history that yeah, the properties of the impactor beyond mass in a hypervelocity collision doesn't really matter, you know, because it is just the impact energy. But yeah, throwing a volatile at it, then you have that added component, which would be kind of cool, especially since we know there are things out there. So nice.
Yeah, I would honestly love help working on atmospheres and adding volatiles in. That's not really my expertise. I've worked with tornadoes before, but tornadoes are a different beast from just particles in an atmosphere altogether. So any help that anyone can give on that project, I'd be happy to collaborate on something.
And of course, comets get impacts too.
Mm-hmm.
Any other questions for Jenny? Oh, Jack.
So what am I? Oh goodness, I'm so dark. Hi, Jenny.
Hey.
Yeah, actually, great talk. I had a question about I think it was on slide 14, your sort of big result figure where you were showing the wasn't this one, it was yeah, that one where you show rotation period to mass ratio. That is interesting. Just the shape you get where it's it's kind of hard to tell with the scale bar, but almost is the beyond the shape itself, is the texture kind of that exists in well, how do I describe it? Like the upper left, there's kind of a texture to the color. So just a number problem, or is it real?
Wow, now I've been looking at this for too long.
Or could
So
it be screen?
yeah, you stare at it and you start to kind of like lose focus a little bit after a while.
Yeah.
That is, so are you referring to like this
Oh, so I mean, it's hard to describe.
here or this here?
Yeah, so in the bump itself, it seems to be that the maximum distance reached isn't clearly dependent on the I mean, it is dependent on the rotation period, but there seems to be some variability within that. But because I'm guessing you're not getting that much. How many particles are you getting in that mass ratio range, actually? I guess.
So I have, for these simulations, I have 500,000 particles that I'm working with.
Okay.
That was because I wanted to run more, but I had 3 months before my defense. So time.
Fair.
Yeah, so this area, like there is some interpolation that I did on this plot itself.
Okay.
I see is part of an issue. I can make this plot without that, honestly, and that would be fine as well. But we do get this kind of bump of like the maximum distance traveled where
Yeah.
the higher mass ratios and the slower rotation period, we are still getting kind of more particles traveling farther.
I mean, it makes total sense to me that you're kind of those particles are hitting that sweet spot. Yeah, where they're what, not so big that they just don't fly, but they're not too small that just go.
Yeah, because at this point, like it's rotating fast enough that your particles are getting swept around the equator. If you're looking at almost exclusively just rotation period, it won't get swept necessarily all the way around the equator, but mostly. Once you add in the mass ratio and like the higher secondary body, it kind of ends up pulling particles. So the particles will get lofted high enough due to the secondary body kind of pulling them off the surface a little bit that it helps them get slung around the equator more.
Okay.
Yeah.
Neat.
That
Really
makes
neat.
sense.
Yeah, makes sense.
Okay.
Awesome.
And
Anyone else?
also, I believe if the impact is close to the pole, rotation pole, the rotation period would have little effect because the velocity imparted due to rotation would be smaller, right?
Yes and no. So you do, yeah, that's tricky because like yes, you are correct. But also if the particles are, if it's a big enough impact and the particles are lofted high enough off, they will kind of still sink down to form a ring around the equator just from the, not necessarily the rotation velocity, but just the angular momentum settling them down along the equator. So yes and no, they do, it does have very little effect at higher latitudes, but it will have an effect if your particles are far off the surface. That makes sense.
Any final questions for Jenny? Hey, Jenny, we really appreciate your time. Great talk.